All right, let's dive right into this explainer. Today, we're going to trace the invisible forces of fluid dynamics all the way from theoretical physics down to building actual physical machines right on your workbench. Because you see, whether you're sizing up a massive industrial air compressor or just gluing PVC pipe together in your garage, the core physics, they remain exactly the same. We're going to totally decode how mechanical energy forces air and liquids to do our bidding. It's going to be a fun one.
Here's our roadmap for the journey today. We'll start with the two fundamental ways to move air, talk about squeezing air through positive displacement, crunch the math of flow, explore how we control that flow with check valves, and finally, we'll get hands-on with building your own pump.
Okay, Section 1. 2 ways to move air. Let's look at how this builds the absolute foundation of all pump engineering.
So, the pump family tree basically splits right down the middle. When you're dealing with fluid dynamics, you are fundamentally doing one of two things. You are either mechanically crushing air into a smaller space, or you're using spinning blades to throw it forward. Positive displacement works by trapping a fixed volume of air in a chamber and then mechanically reducing that space. Think of a piston slamming into a cylinder. Dynamic pumps, on the flip side, continuously accelerate the airstream to super high velocities using impellers. They don't trap the air at all. They literally just impart kinetic energy right into it.
Now, for those dynamic pumps, Euler's turbomachine equation is the absolute baseline. It's a mathematical principle that proves the work done by a spinning impeller translates directly into a useful alteration of the fluid state. Basically, fluid enters the center of an impeller axially, gets rotated 90 degrees, and is accelerated outward by centrifugal force. The pump is quite literally converting the mechanical shaft power of the motor into kinetic velocity, which a stationary casing then smoothly converts into static pressure. It's this elegant, continuous flow, but it behaves very differently from our other pump family.
Moving on to Section 2, squeezing air, positive displacement. Let's see how we apply these heavy-duty forces to the workhorses of the industrial world.
Let's break down how positive displacement actually functions inside a reciprocating pump. Honestly, you can just think of a reciprocating compressor as a 4-stroke engine running in reverse to physically trap and squeeze the air. First up is suction, where the piston retreats, the internal pressure drops, and fresh air gets sucked in. Next is compression. The piston reverses direction, the internal volume shrinks, and pressure spikes. Once that internal pressure beats the pressure waiting in the tank, we hit the delivery phase, forcing the air out. And finally, expansion. A tiny bit of trapped air at the very top of the piston expands back to normal pressure before our brand new suction cycle can kick off. Now, when you're ready to actually buy one of these machines, your specific needs dictate the price tag. A high-tolerance rotary screw compressor costs 4 to 5 times as much as your standard garage piston pump. Why? Well, a reciprocating piston compressor is cheap and easy to rebuild, but it's incredibly loud and limited to about a 50 to 75% duty cycle. It literally needs time to rest and cool down. But a rotary screw? Because it uses intermeshing helical rotors with insanely tight clearances, we're talking around 0.05 millimeters, it can run continuously at 100% duty cycle. And if you need absolutely zero oil contamination, like say in a dental office, you have to move to a scroll compressor. The takeaway here? You match the machine to the work, not just the specs on the box.
But what if you need just an immense amount of pressure? By using differential piston sizes, where the air motor piston has a much larger surface area than the pump piston, these air-operated pumps can multiply standard 100 psi shop air into a staggering 7,000 psi. That 70-to-1 ratio is an absolute game changer. It allows factories to push incredibly thick, heavy NLGI3 greases through massive industrial lines without breaking a sweat.
Which brings us to Section 3, the math of flow. To properly harness all this mechanical power, we have to understand the math dictating their efficiency.
You see, it's a very common misconception that simply spinning a compressor faster automatically gives you more air. It doesn't. Enter volumetric efficiency. This tells us how much air the pump is actually delivering compared to its mathematical physical volume. As your compression ratio goes up, or, and this is key, as you spin the pump too fast for its internal valves to physically keep up, your volumetric efficiency is going to drop off a cliff.
Let me paint a picture for you with a real-world example of volumetric efficiency in action. Imagine a shop owner trying to run a 14 CFM paint spray gun on a compressor that physically can only produce 6.09 CFM at its standard speed. Naturally, they think, I'll just swap the pulleys and spin it up to 1200 RPM. Well, actually, nah, scratch that. When they do that, the volumetric efficiency drops from 85% down to 75% because those internal reed valves simply cannot snap shut fast enough.
They still only get about 9 CFM, the pump head temperature spikes to 195 degrees Celsius, and the pump completely destroys itself. It's proof that you can't just slap a bigger motor on an undersized compressor head, you need a bigger pump, period. Or at least a much larger storage tank. $1,200. Yeah, you heard that right. That is the shocking annual cost in wasted electricity for a single, tiny 3mm compressed air leak at 100 psi. Because only about 10 to 15% of the electrical energy put into an air compressor actually reaches your tool as useful work. The rest is just lost, primarily to heat. Compressed air is an incredibly expensive utility. This highlights exactly why system efficiency and hunting down those annoying hissing leaks matters so heavily to your wallet.
And honestly, this isn't just about saving cash. It is fundamentally about physics and safety. The hard engineering facts tell us that failing to drain compressor tanks leads to severe, catastrophic incidents, like the 1989 Henderson Peak CONPO arc explosions. Compressing humid air condenses out massive amounts of liquid water. We're talking sometimes over 6 liters a day if you live in a humid climate. If you leave that in a steel tank, it rusts from the inside out until it literally ruptures. That makes OSHA safety standards, like daily draining and mandatory 10% safety relief valves, absolutely non-negotiable.
Section 4. Controlling flow with check valves. Let's transition over to the tiny gatekeepers of our pumps that force all this air and fluid to only move in one direction. From heavy-duty steel flaps failing under extreme heat all the way down to zero-friction silicone membranes in microscopic labs, getting the right seal dictates the success of the entire system. In a standard shop compressor, you've got 0.2mm spring steel reed valves that slap open and shut thousands of times a minute. Over in heavy hydraulics, you'll find U-cup seals that cleverly use the fluid pressure itself to flare the seal tight against the cylinder wall. And in microscopic lab-on-a-chip medical devices, traditional mechanical valves are just way too sticky. They require trapezoidal, zero-gap PDMS silicone valves that flex flawlessly without rubbing the sides. The scale changes drastically, sure, but the fundamental job of trapping pressure remains exactly the same.
All right, Section 5, building your own pump. Let's roll up our sleeves, leave the industrial factory behind us, and apply this theory directly to the DIY workbench.
I absolutely love this quote from the Tinkering Idiot blog. Failure is not an option, it's the baseline. It sets the perfect low-stakes tone as we transition into literal garage engineering. Because let me tell you, when you take industrial fluid dynamics and try to apply them using off-the-shelf hardware store plumbing parts, you're definitely going to encounter some frustrating realities about manufacturing tolerances.
Case in point, what I call the O-ring dilemma. If you try to build a custom check valve using a standard 3/4-inch PVC slip adapter, a rubber O-ring, and a steel ball bearing, you'll quickly find out that not all PVC is created equal. A Genova brand fitting has a slightly smaller inner diameter that actually holds the O-ring nicely, but Lasco and Charlotte pipe fittings, they are just a bit wider inside. It turns out relying on standard plumbing tolerances for custom check valves will quickly send a steel ball bearing shooting across your garage, literally like a bullet, simply because the O-ring can't retain it. So, how do we actually fix this without a machine shop? By ditching the fiddly O-ring for a standard rubber garden hose washer. The wider outer diameter of the washer allows it to be perfectly pinched between the PVC pipe and the fitting. You just drop your steel ball bearing on top and then use a piece of ordinary weed whacker line drilled right across the pipe as a retaining bar to keep the ball from flying away. Just like that, you've built a flawless, dirt-cheap check valve that holds low vacuum pressures and works perfectly for DIY pumps. And you know, you can take this whole concept even smaller. You can apply these exact same positive displacement principles to medical plastic, creating a highly functional manual pump for mere pennies. By taking a 5ml syringe, placing a miniature steel ball inside, and capping it with a cut piece of a smaller 2.5ml syringe, you create a perfect gravity-seated poppet valve. Connect 2 of these together with some tubing and a dab of hot glue, and you have literally built a working air compressor out of desk drawer supplies. It's that simple. So now that you understand the invisible forces of dynamic kinetic energy, the mechanical workhorses of positive displacement, and the tiny check valves that control it all, I have a challenge for you. Spot the fluid dynamics hiding in plain sight. From the AC unit humming away outside to the tiny dispenser on your soap bottle, how many pumps did you rely on today before you even left your house? Keep learning, keep tinkering, and I'll see you in the next explainer.